So this is going to start us then with our first technical topics for the class, which, again, as I mentioned, we're going to start with the switching exam, to go through all of the layer 2 Ethernet switching features and functionalities, and then most likely on Wednesday we'll get to routing. The first topic then is going to be based on the overall general network design for layer 2 Ethernet networks, which is sometimes called the campus network design or the hierarchical campus design, where the idea behind this is that Cisco separates their layer 2 switching design into a 3-level of hierarchy, which basically is going to give us smaller building blocks of the network that we can combine together in order to scale the network and to make it a little bit more manageable. The 3 categories, the 3 levels of hierarchy that they separated into are the access layer, the distribution layer, and the core layer, where sometimes the distribution is also known as the aggregation layer, and sometimes the core layer is also known as the backbone. Basically what this means is that your end hosts, which would be like your PCs or your phones or your printers, whatever the devices that are network attached, they're going to be connecting to the access layer. From the access layer, we're going to have then these access switches that are typically connected to the distribution, which is aggregating not only the number of ports, but also the bandwidth in the network. And then it's ultimately going to be sent to the core layer of the network, which is going to be the main interconnection between different either geographic regions or different like functional units of the network. So if we were to visualize this, the idea is that the port density for connecting to the end host, this is what's happening down at the access layer. Then typically we're going to have 1 or more connections up to the distribution layer. This is where we would be running typically like our layer 3 routing, or maybe redundancy protocols like HSRP or VRRP, or maybe any type of traffic filtering. Usually the access layers is just for basic attachment, like where our VLAN assignments would be, or where the spanning tree protocol domain would start. Where the core of the network, this is where we're trying to just basically do forwarding between different segments. So we don't want to bog the core down with additional features like application level traffic classification or any type of filtering or any real advanced features. This is just trying to get traffic from point A to point B, like we could be attaching to the WAN, or we could be attaching maybe to the data center, where typically the core is going to be to aggregate the physical different points of the network together. Now the reason we want to do this to begin with is that the main advantage, it's going to allow us to scale the network. So if I want to add a new portion to the network, I don't have to redesign the entire thing in order to do this, because the only thing I need to do is just add a small access layer or add a small new distribution block. So it's going to make the network design more scalable. We'll also see that this is going to impact what's known as the failure domain of the network. Or if one of the devices goes down, let's say there's a physical link cut or one of the switches crashes, by separating them into these different layers, just because one portion of the network fails doesn't necessarily mean it's going to affect everything else in the topology. So when we get into some of the interaction between the layer 2 LAN and the layer 3 routed network, this is one of the big design considerations, that if my network is built wrong, I could have a host that has something wrong with its NIC card, and maybe it's sending like a broadcast storm out to the network. I want to make sure that that's not going to take my whole data center down because one endpoint is broken. The other thing is that it's going to help us in troubleshooting and trying to manage the network. So not only management from a physical layer 1 point of view, like how is the cable plant installed, but then when we look at like aggregating the device's configurations or adding new changes to the network, when you build it in these levels of hierarchy, it makes the overall network design a little bit easier to manage. There's a couple documents I want to mention here that go along with Cisco's general design theory for this. If you search for the design zone, and the design zone is what they used to call the Solutions Reference Network Design Guides, or the SRNDs. sometimes this is also called the Cisco Validated Design, or the CLD. Basically what this is that before they take some new technology and try to deploy it in a large scale, they have all sorts of testing that goes on behind the scenes, and they try to build like scale models of the network to see what the end result of it is, and what's the best way to build the network together, and the best way to configure it. So under Design Zone, if you were to go to borderless networks, is what they call this now. This is basically the enterprise network. And under Campus, this is generally what's talking about the layer 2 switched network, the layer 2 LAN, or also layer 2 wireless access, so like our Wi-Fi interacting with the Ethernet LANs. And under here, there's a couple good design documents. One of them is the Borderless Campus Design Guide, which basically is just a big PDF that talks about different portions of the network and how they fit together, where the network design principles and models, this is going to talk about like the different layers of the network, or if we look at the multi-tier, it talks about the core layer versus the distribution layer versus the campus layer. But also what's nice about this, when you actually go to deploy these technologies, they give you a lot of configuration templates that you can use to figure out what would be the appropriate configuration of your layer 2 access switches, as opposed to your layer 3 distribution switches and then your routing in the core. So we'll come back and reference this as we get to different portions of the network, like how is EHRP routing going to play into the layer 2 LAN, or how could we use OSPF routing instead. Also high availability. This is going to be for stuff like our HSRP or VRRP or GLBP designs. Then also deploying QoS for application performance. This would be like dealing with our IP telephony or our voice over IP systems, or maybe some sort of video conferencing or multicast video that we have going over the LAN. This is kind of just the overall picture of what they're trying to say. These are the different products that we have, and this is how it fits into our design model. There's also another one here that is the High Availability Campus Network Design Guide. We'll talk about this in more detail when we get to some of the layer 3 routing protocols. But this one here is really good, the Campus Recovery Analysis Design Guide. This shows how you could figure out, based on how your network is built, if one portion fails, what is going to be the result of that? And what are the individual protocols that come into this design that are ultimately going to control, if there's a problem in the network, what's the result of it? Like it talks about, you could have a case where you're running HSRP, you're routing with EHRP, and you're doing per VLAN spanning tree protocol. If a failure happens, what's the result of this from a restoration point of view, or what's sometimes called the network reconvergence process? So basically, when the network topology changes, how long does it take the network to self-heal around that? Or how long does it take to figure out that the change happened and then to change layer 2 switching or to change layer 3 routing in order to get the new correct agreement on what the topology looks like? So depending on what the layer 3 protocols are and how these interact with our layer 2 protocols, like we'll talk about the differences between rapid spanning tree versus the legacy per VLAN spanning tree or the legacy common spanning tree. Also, when would you want to run HSRP versus GLBP? Also, how could layer 2 looping come into the design? So some of this stuff may be above and beyond the scope of the switch exam or the route exam, but from a practical point of view, this is where you can get a lot of help for the actual deployments of these networks. So when you're in your designing stage and then when you're in your implementation stage, how has Cisco recommended to do it over the years, and then what's the result that they've come up with for these type of testings? So if we look at some more specifics of the individual pieces that are making up this model, again, the last portion of the 3-level design, or the 3 levels of hierarchy, is the access layer. And this is going to be the entry point for the applications. So our desktops, our IP phones, our printers, also like the wireless access points, generally these are going to be connected at the access layer. Historically, this has been generally made up of layer 2 Ethernet switches, but in today's networks, a lot of times it's also layer 3 switching as well. So we'll look at some design cases when we get later to routing with like eIGRP and OSPF. There's cases where you could pretty much do away with layer 2 switching almost completely, except for the devices in the same VLAN on the access layer, and then use routing protocols in order to do the path selection and to do any of the convergence in the rest of the network. The main idea behind this is that once we go to send traffic to other portions of the network, we need some additional layer of hierarchy to kind of aggregate our bandwidth together or aggregate our connections together. And this is what the next level is, the distribution layer. So typically we're going to have multiple connections from access to distribution so that if there's a physical link cut or one of the physical switches goes down, we're able to rebuild the network or to re-heal or reconverge around this. By far the most common feature of the access layer is going to be the broadcast domain segmentation, or what we call the virtual local area network, or simply the VLANs. We'll see that the VLAN ultimately is going to control on the Ethernet LAN who are the hosts that you can directly talk to without having to go to a router. So if I were to send an address resolution protocol request or an ARP request, the broadcast domain would control who actually gets that request when I send it. The other thing is going to be for the quality of service marking, or what we'd sometimes call the classification. And in today's enterprise networks, this is going to be a big feature that we need to make sure is properly enforced. Because if I have my phones for the voice traffic now going over the Ethernet LAN, I want to make sure that someone doing like an FTP download or doing web browsing is not going to cause someone else's phone call to drop. So as the traffic actually enters the access layer, this is one of our big considerations for switching. We need to make sure that the different applications, I'm able to tell the difference between them in the network. And the way that we do this is with what's known as the packet marking, or the packet classification. This is what's sometimes defined as your trust boundary. So whether the layer 2 switches or layer 3 switches, when they allow the traffic in, are they going to leave the classification up to the application, like the actual phone itself, or whether they're going to try to enforce this themselves, like change different types of packet markings. Another key feature is going to be the security of the network. In a lot of networks nowadays, this is where we run a protocol that is known as 802.1x, which basically means that when I connect my wired PC or my wired whatever to the LAN, it's going to ask me for authentication information. It could be based on simply a username and password. It could be something like a one-time password, like an RSA secure ID, where you have one of those physical dongles that you plug into your machine, and then that allows you to get onto the network. This is mainly what the job of 802.1x is. To take our authentication databases, if we're running like Windows Active Directory or some sort of other authentication mechanism, we need to get that to talk to the access switches to see who can actually get onto the network to begin with. In the case of the wireless LAN, this is where we would be doing our layer 2 wireless security, like are we running WPA2, are we running the personal version, which is just a username and password, are we running the enterprise version, which could use like the secure IDs. But the key is that this is happening on the first step of the network. If there's someone that I don't want to get access to the network, I want to try to do that as early as possible in the topology, so down to the access layer. We'll also see that there's a bunch of other common layer 2 security holes in Ethernet LANs that we need to deal with. This is where protocols like dynamic ARP inspection would run, or the DHCP snooping feature, or the IP source guard. We'll talk about those in more details when we get to layer 2 security. But basically, this is preventing someone from plugging into your network and then doing some sort of attack where they can redirect traffic to them, or they could knock someone else off of the network. We want to make sure that we can enforce this right at the entry point of the network, right at the access layer. Another key thing would be for multicast traffic management. If we're running some multicast application, like let's say that you're running like Norton Ghost to do different images for your desktops, or you're running something like a video application that your end hosts are watching, I want to make sure that when that traffic actually gets down to the last segment, down to the access layer, that it's only going to the host that actually want it. Because otherwise, if I don't manage my traffic with multicast, multicast basically becomes broadcast, and this kind of defeats the purpose of running a multicast application to begin with. That I want a case where I have one sender, but many receivers, a one-to-many type of routing paradigm or traffic paradigm we sometimes call, as opposed to a unicast communication, which would be one-to-one, or in the case of broadcast, which would be one-to-all. Last but not least, this is where also your inline power would run. So for your IP phones or for your access points or other network equipment that can get its electricity from the network cable itself, this is what the access layer is going to be in charge of. It's what's known as inline power. Next level of hierarchy is the distribution layer, or sometimes called the aggregation layer, where the idea is that we're taking all these connections that go down to the endpoints and we're combining them together into higher bandwidth links. So if I have 1,000 endpoints in the network, I don't need 1,000 cables that literally run to the core of the network. So we're trying to combine them together in a smaller number of links, but generally higher bandwidth of links. Where a lot of times this is going to be where our layer 3 operations are going to run. Where the end host, when it looks at its default gateway, it could be pointing at the distribution layer. So this is going to be our separation, or what we sometimes call the demarcation, between the layer 2 network and the layer 3 routing network. Typically you'd see that you have multiple connections that go up to the core and also multiple connections that go down to the access layer. So if there's a physical link failure, I'm able to reroute around that or make a layer 2 decision in order to use like spanning tree to choose one link over the other. Or likewise, if one of my core switches goes down, that it doesn't take out the entire network, because I have multiple levels of hierarchy here. Some of the key features here would be the redundancy of the network. So as I mentioned, are what's sometimes called the first hop redundancy protocols, or the FHRPs. We'll see there's different variations of these that have different features. Like HSRP is a Cisco-specific implementation, where VRRP is an open standard. So there may be some designs where you want to use one versus the other. But the overall idea behind this is that if one of my distribution switches goes down, from the end host perspective, they're not going to know that. They're able to still send their traffic into the network. They're able to still make their phone calls. And it's not really going to affect that one of the physical portions of the network is down. Another key point is going to be the aggregation of the bandwidth. So if I have multiple fast Ethernet links, or I have multiple gigabit Ethernet links going down to the access layer, when I start to add all the bandwidths up, if I have the same connections in the distribution, it means you're going to have a lot of oversubscription of the network. Or basically when not everyone can send at 100% link utilization at the same time, because the bandwidths don't add up together. So this is where a protocol that's known as Ether channel, or the standardized version of this, which is defined by 802.3 AD, is used, which allows us to take multiple physical links and then combine the bandwidths of them together. But from the network point of view, it's going to look like one logical link, or one link for sending either the layer 2 or the layer 3 bandwidth. Where a lot of times in today's designs, what you may see, like in the case of like a data center network, is that at your access layer, when I'm going down to my end hosts, this connection here may be like gigabit Ethernet. Where if the hosts are now gig-E attached, which means they can send at 1,000 megabits per second, or 1 gigabit per second, if I have 48 ports that are facing downstream towards the actual end hosts, when I connect up to my distribution switches, let's say I have distribution switch 1 and distribution switch 2, if I have potentially 48 gigs of bandwidth going down to the access layer, it doesn't make sense that these uplinks would be fast E, or maybe even that they would be single gig E. So in a lot of times with newer equipment, you may find that these uplinks are going to be 10 gig E. And there's new standards that are available to get us to 40 gig E. And then also the very newest ones that are coming out go up to 100 gig E, where we're trying to combine the bandwidths of the end hosts and then send them upstream towards the distribution. Where again, in this case, that if this physical switch failed, I should be able to transparently reroute my traffic to the other switch, and then the network or the end hosts are not actually going to know that that failure occurred. So again, with the last point with the bandwidth aggregation, if you don't have these huge bandwidth links, 40 gig E or 100 gig E, because these are still really, really expensive, you may be taking smaller ones, like let's say we have single gig E, but now I have multiple attachments, where I have 2 ports that are going from access to distribution, but I'm combining these together into a 2 gigabit per second link. This is what we do with either the Ether channel feature or the standard version of it, which again is called the 802.3 AD. Some vendors also call this NIC teaming, where your end servers could also run this, like your VMware machines or your Windows or Linux boxes. When they attach to the network, they could have multiple physical links, but they combine that together to look like it's one logical circuit. And this is the advantage of 802.3 AD. There's an open standard that anybody can implement it if they want to. Another one is going to be load balancing. That if we have that same type of design where there's multiple access switches, let's say access 1, access 2, 3, and 4, and these are then connecting to distribution level switches, let's say distribution 1 and 2, and I have all sorts of meshes of connectivity to try to avoid the case where if one switch goes down, I can reroute around this. I may want some of my traffic to go this direction and some of my traffic to go this direction, which is sometimes called either load sharing or load balancing or load distribution, where some of the traffic goes one physical path of the network, some of the traffic goes the other physical path. There's different types of protocols that we could use to accomplish this, whether we're dealing with like layer 2 spanning tree or layer 3 routing, like with EHRP or OSPF. There's different considerations we'll see from not only a design point of view, but also the actual implementation point of view, how we need to account for those. This is also going to be used at the distribution layer for what's known as topology summarization, or which is sometimes called also aggregation. And topology summarization generally is going to be talking about your IPv4 addressing, where down to the access layer, typically on a VLAN to subnet basis or an IP subnet basis, we're going to have a one-to-one relationship where if hosts are in VLAN 10, they're going to be in the same subnet. And if hosts are in VLAN 20, they're going to be in a different subnet. So as these IP networks start to get advertised up to the layer 3 network, one of the things that we can do is try to hide the details of the network topology to make the devices in the core of the network have a much simpler decision of how I route traffic from point A to point B. Where maybe I have 10,000 hosts that are attaching to the network, and I have 1,000 different VLANs, which means I have 1,000 different subnets. Maybe in the core of the network I could try to minimize this number, where maybe I can get it down to 100 subnets or 50 subnets or something smaller, so that when the core makes their forwarding decision, they don't have to look at 100,000 routes in the routing table, or look at some huge layer 2 MAC address table in order to figure out how do I actually switch the traffic. Where the bandwidth aggregation, this is going to be a physical function of the network, a layer 1 aggregation. The topology summarization, usually this is a logical layer 3 summarization. So as we get to our details of EHRP, BGP, and OSPF, we'll look at the different ways that we can do that, hide details of the network, and then end up with less complicated decisions. Then lastly, we have the core of the network. This is what's also sometimes known as the backbone, where the idea behind this is that we want it to be able to forward just as quickly as possible and be as reliable as possible without having to run tons of software features. Most of the time, this is going to be our hardware accelerated layer 3 switches, like Catalyst 6500 or 7600 series router, or like the Nexus 5000 or 7000 switches, something that has lots of bandwidth capability and can just switch as quickly as possible between the different segments of the network. Idea behind this is that we generally want to get line speed or wire speed forwarding. That if I have physical links that are 10 gigabits per second, I want to make sure that I can actually get my links to be like 95% utilized or potentially 100% utilized, where that there's not a difference between how fast I can forward in software versus what the hardware of the interface is. Also, a big key behind this is that if a failure happens of a physical link or a physical node, like another switch or another router, we want to try to reconverge around this as fast as possible, or basically reheal the network. A lot of times this is going to be based on your layer 3 network design with things like eEdgeRP or OSPF, or a feature that is known as MPLS traffic engineering and the fast reroute feature, where typically this is historically a service provider feature, but you can also implement this in the enterprise to avoid the case where if one of my switches goes down or one of my core routers goes down, I can immediately make a new decision and then try to reroute around this. Where in certain cases you can get traffic engineering to heal the network in about 50 milliseconds. For eEdgeRP and OSPF, you can get somewhere around 1 second or maybe less than that. Really depends on what your application needs are. If you're dealing with some sort of financial network that is actually accounting packets like down to the microsecond, then this is really going to be a big deal. But if you're just an enterprise network and you want to make sure that if someone is on a phone call, the phone call is not going to disconnect, then usually that's a lot easier to solve than some of these really extreme examples. So in our case, we're mainly going to be focusing on how do we do this with the layer 3 routing protocols, or how do we do this with like layer 2 spanning tree. Another one is going to be the bandwidth utilization, where one of the big problems in the core of the network historically is that when you start to add up all the connection speeds of the access layer or the distribution, that if you don't have enough bandwidth in the core, you're not actually going to be able to use the full capability of the network, which is sometimes also called oversubscription. Which basically means that we're going to try to guess for cases where not every single host is going to send 100% of their link speed at the same time. Or if someone is making a phone call, they may only need like 64 kilobits per second of bandwidth. I don't really need to offer them gigabit Ethernet, where they're going to send it 1,000 megabits per second. But this is one of the big design considerations we need to take for the core of the network is how are we actually going to distribute the bandwidth between different portions of the topology. Okay, any questions so far? Yep.
On the MPLS fast reroute, is that like a layer 2 or layer 3? Are you using label switching?
It's with label switching. It's kind of both at the same time.
Okay.
Basically, the way that it works, and this is not going to be in the scope of the exam, but it's kind of a cool feature to know that there's a lot of interesting problems that you can solve with it. But let's say that you have like a core router 1 that is attached to router 2, to router 3, and to router 4. And I'm trying to get my traffic from point A to point B. So I have two different ways that I can go in the network. I could either go from 1 to 2 to 4, or I could go from 1 to 3 to 4. What you can do with the the traffic engineering, and specifically the fast reroute, which is sometimes called link and node protection, which basically means that from point A to point B, I'm going to try to send my traffic this direction. But before I send the traffic, I know that ultimately I'm going to be leaving the network via device 4 or by router 4. So I can pre-calculate a backup path that goes another direction. So if this device goes down or this link goes down, I can immediately switch over to the pre-calculated path as opposed to waiting for OSPF or waiting for EIGRP to make a new decision. So you end up in this design where you try to take almost every possible failure into account. And you say, if this link goes down, then you're going to go that way. If this router goes down, then you're going to need to go through these other 2 hops in order to get there. But the key is that this device basically has pre-calculated those failure scenarios. So if it happens, it can switch over really, really fast. So next thing we would then need to talk about is what are the different devices in the network and how do they fit into these different categories, the access, distribution, and core layers. Where in the case of Ethernet LANs, this is typically where we're going to be talking about some of the legacy devices like our hubs or our repeaters or multi-port repeaters. This is also traditionally where our layer 2 bridges would sit, where today is going to be taken over by the role of our layer 2 switches. Also, we have our regular layer 3 routers that would be running like IP routing or IPv6 routing. And then also a combination of these, which could be like layer 3 switches or layer 3, layer 4 switches, that as the layers go up of the OSI model, basically means the device is making a decision based on more complicated inputs, or it has more visibility of like, is this a TCP session between web servers versus a phone call between a source and a destination? And you'll see that for a lot of devices nowadays, they can make their decision not only on the layer 3 header, like the IP destination, but also by the layer 4 information, like the TCP port or the UDP port. And we'll see that the routers actually do this by default. We'll talk about that more when we get into layer 3 routing. So the first of which, the hubs and the repeaters, this is what we consider to work at the first layer of the OSI model, which is the physical layer. Where the idea behind a hub or repeater is that it's going to take the physical electrical signal that it's receiving, and as it comes in, it's just going to amplify it out all of the other ports, or basically repeat it out all of the other ports. Where a hub is sometimes known as a multi-port repeater. Now, the disadvantage of this is that these devices are typically unintelligent and unmanaged, which means that they don't accept any configuration from us or don't accept any management from us. They're basically just a layer 1 physical device. It would be kind of like if you're trying to amplify your TV cable signal. If you plug in an amplifier, it's basically a single port repeater. It's taking the electrical signal as it comes in and then repeating it or generating it again as it's going out. The main disadvantage of this in terms of Ethernet networks is that it doesn't make a decision on how it's going to send the traffic. Just for every type of traffic that's coming in, it's just going out in all the other directions. What this means is that devices connected to a hub are in what's known as the same collision domain. And this has to do with a physical layer 1 and layer 2 contention mechanism of Ethernet that says if I want to send a frame onto the layer 1 network, I have to check to make sure no one else is sending first. Which in the case of Ethernet, this is called our carrier sense with multiple access and collision detection, or CSMACD. This is only needed in half-duplex Ethernet networks, because in full duplex networks, which we'll see with our switches, it means that all devices are in different collision domains. But if you were to use a hub, or what we'll talk about later, like in the case of wireless with Wi-Fi, everyone in the wireless channel is in the same collision domain, and they all have to contend for the same bandwidth, or try to share the bandwidth between them. This also means that everyone is in the same broadcast domain, which we'll see the broadcast domain is ultimately going to control when I send an Ethernet frame out, a layer 2 packet, who could possibly receive it. So in the case of IP version 4 over Ethernet, we need to do our IP version 4 address to our layer 2 MAC address mapping, which is going to be done by what protocol? It is going to be done by ARP, the Address Resolution Protocol. So a broadcast domain would basically then control, when you send out an ARP, who's actually going to get it. Only devices in your same broadcast domain will be able to receive that, because from an Ethernet transmission point of view, we're not going to be forwarding broadcasts between different VLANs, or routers are not going to forward broadcasts between different routed segments. So in the case of the hubs and the repeaters, not only are they sharing the same physical wire, which means they're in the same collision domain, they're also part of the same logical layer 2 network, or they're part of the same broadcast domain. Next one up from there would then be the layer 2 bridges, or layer 2 switches, where the idea behind this is that we want some more intelligence going down to the access layer, and we're going to be forwarding our frames based on layer 2 addressing, or essentially based on our layer 2 MAC addresses, as opposed to just regenerating the electrical signal out all of the interfaces. We'll see when we actually get to the layer 2 switches, the way that they do this is by using a table that is known as the CAM table, or the Content Addressable Memory. This is basically a layer 2 switching table that's going to hold all of the MAC addresses of the network. So the CAM table, or the MAC address table, is ultimately going to be how the switches decide how they send their traffic, or how they forward their traffic.
So CAM table and MAC table are...
Means the same thing, yeah. We'll see that when we talk about some of the WAN medias, like frame relay or ATM, there's also switches that use this same type of logic, that as a packet comes in, or as a frame comes in, I'm going to make the decision based on the layer 2 address where it's supposed to go to. Where in the case of frame relay, it would be doing this based on the data link connection identifier, or the DELC address. In the case of ATM, it uses what's known as the virtual path identifier and the virtual channel identifier, or the VPI/VCI. These two are basically the equivalent of MAC addresses, but for a different layer 2 protocol. So a bridge or a switch, it doesn't necessarily mean Ethernet, but it's the same type of logic, that we're making the decision of how traffic is sent based on these different types of layer 2 addresses, or what we sometimes call the hardware address. Now the key is that when the layer 2 switches make their forwarding decision, and then when they actually send the traffic, they don't actually change anything in the packets, or in the layer 2 frames. This is why Ethernet switching is also known as transparent bridging, where when we compare the layer 3 routers versus the layer 2 switches, layer 2 switch doesn't change anything when traffic is moving from point A to point B, where a router is going to be changing the traffic every time it moves it between an interface. It's going to be building a new layer 2 header, like if I'm going from Ethernet to frame relay, or I'm going from wireless to Ethernet, the router's going to have to change the frame formats, which is sometimes known as the layer 2 packet rewrite. But layer 2 switches don't do this. The only thing they need to do, know is where's the packet going, what's the destination of it, and then it's going to move it out a different interface based on this MAC address table, or the CAM table. We'd also typically see that the layer 2 switches are going to be hardware accelerated, which use the ASICs, or basically a hardware implementation at the chip level of the forwarding logic to move the packets between the interfaces. A lot of times this is why you'll see that a layer 2 switch would be able to do forwarding at line rate, like at a gigabit per second or potentially 10 gigs per second. But when you start to get into the layer 3 routing, even though you may have a gigabit Ethernet link on a router, most of the time it's not going to be able to send that fast. And it's because it has to make a more complicated decision as it actually sends the traffic between the interfaces. Now when we're connecting to our layer 2 switches, or our layer 2 bridges, we would consider the devices to be in the same broadcast domain. And we'll see it in more detail a little bit later. There's ways that we could change this, like changing VLAN assignments, or in the cases of like Framula or ATM, we would have different virtual circuits. But from a most simplistic point of view, if you take like an unmanaged switch and plug all of your devices into it, they should all be able to send layer 2 broadcasts to each other, or be able to do like that IP address to MAC address resolution with ARP, because they're going to be in the same broadcast domain. The key difference, though, is that they're not in the same collision domain. So in the case of switches, we can run the Ethernet LAN, or the individual ports, in what we consider full duplex mode, which means that there's a different wire that I use to send my traffic than I use to receive my traffic. So I can send and receive at the same time, because from a layer 1 physical point of view, it's using different cables. Whether it's a copper link that's using different twisted pairs, or whether it's a fiber link that uses a different send fiber versus a receive fiber, full duplex just means you can send and receive at the same time. When we talk about wireless networks with Wi-Fi, they always have to run in half duplex, because your radio can either transmit or receive, but not both at the same time. And this is one of the big limitations of Wi-Fi, that it's a half duplex media. You have to contend with all of the other devices for the bandwidth in the air. So as I mentioned, the layer 2 switches, like the Ethernet switches, what they are mainly going to define is what we consider the broadcast domain, or basically who can directly talk to each other over Ethernet. From an Ethernet low-level point of view, this is what's controlled by the specific destination address that is all Fs. So in the Ethernet frame, we have a source address and we have a destination address. So where is the packet coming from? Where is the packet going to? Just like we do in IP networking, where we could have a one-to-one communication, which would be unicast. So from one source to one destination, we could have a one-to-many, which would be a multicast. We could have a one-to-all, which would be a broadcast communication. Both layer 2 networks and layer 3 networks have this notion, where in the case of Ethernet LANs, there are unicast MAC addresses, which would normally be your MAC address that's assigned to your NIC card. There's also multicast MAC addresses that we would use if we're trying to listen to a video feed, or we'll see like when we try to run routing protocols like OSPF or EHRP, those use multicasts, where a broadcast is going to be from one source to all destinations at the same time. In the case of a layer 3 broadcast like with IP, this would be the all 255 address. In layer 2 networking, this corresponds to the all Fs address. So when I send an ARP request, or when I send some other type of layer 3 broadcast, it means that the layer 2 switches are going to be changing it into this destination, this layer 2 MAC address, broadcast address. So the idea behind this transmission is that when the switch receives it, it always looks at the destination MAC address, and based on that, it's going to figure out where do I actually want to send this. If the destination is the all Fs, the broadcast, the frame is going to go out all of the ports that it has in that broadcast domain. So it's going to go out all ports except the one that it came in on. And this is what we consider the flooding procedure, or MAC address flooding, or layer 2 flooding. Where the idea behind this, or the ultimate goal, is that this is how the Ethernet switches figure out what does the topology look like. So where are the hosts actually located? And when I send traffic from host A to host B, what is the port that it's supposed to come in on, and what is the port that it's supposed to go out on? And it does this based on this automatic broadcast flooding. Now in cases of unmanaged switches, which basically means something that you don't configure, you just plug it in and it automatically works, all of the ports are always going to be in the same broadcast domain. But in our cases, we're going to be dealing with managed switches, which means that we can log into the switch, make configuration changes, change all sorts of different options in administration. We then have control over what are the broadcast domains. And this is what the switches define as the virtual local area networks, or the VLANs. So from a flooding procedure, when the switch is going to receive this layer 2 frame that's going to all Fs, it's going to go out every port except the one that it came in on, but only ones that belong to that same VLAN. And when we look at the difference between the access layer and the distribution and the core of the network, this is one way that we can ensure that traffic on this portion of the network isn't necessarily going to affect traffic in another portion. So by changing not only the collision domains, upgrading from hubs to switches, we can manually define what are the broadcast domains and eventually control who can talk to each other directly with layer 2 Ethernet. We'll see the key difference between the layer 2 switches and the layer 3 routers is that frames that are in the same broadcast domain or in the same VLAN, those are going to use layer 2 switching to reach each other. But for destinations that are in different broadcast domains or different VLANs, those are going to need to use layer 3 routing. We'll see cases where the switch has both layer 2 VLANs assigned, but then also has layer 3 routed interfaces, where if I were to have a case where I have some hosts, A and B, that are in VLAN 1, and they're connected to a switch. If they want to reach other hosts that are in VLAN 2, the switch is going to have to make a layer 3 routing decision in order to move traffic from one broadcast domain to another, where if these were in the same VLAN, it would be using just its layer 2 switching, or in other words, the MAC address table, in order to make its decision. So which one it's ultimately using is going to affect different portions of the design. It's going to affect, if there's a failure in the network, how long does it take me to figure that out and to heal around it, because the layer 2 protocols are going to use different convergence techniques than the layer 3 protocols are. Question?
Just so I'm clear, for the layer 3 routing on the switch, you're actually referring to SVIs, right?
Correct, yeah. So when we actually get to the configuration of this, the layer 3 routing, sometimes this is called multi-layer switching, or MLS. This is kind of a legacy term that refers to basically, I have a VLAN interface that has an IP address assigned, and then I can use that to route packets between different VLANs. Sometimes these VLAN interfaces are called SVIs, or switch virtual interfaces. So when someone says interface VLAN, that's what they're talking about, is a layer 3 routing interface that the switch has assigned. But we're going to get into more details about this. Question?
It's accidentally you configure the router to switch, right?
Right.
And you assign, the same IP address, but they are on different VLAN accidentally. Would that be considered the same broadcast domain now, even though they have the same IP address?
Okay, so the question is, if there's two hosts that have the same IP address, but they're in different VLANs, they're going to be in different broadcast domains. So when we look at the specifics behind this, the assignment of who can talk to each other directly at Ethernet or directly over the broadcast domain, this is always based on the VLAN number. So there are actually valid cases where you can have two hosts with the same IP address, but as long as they're not in the same layer 2 network, that's going to be fine. But we'll see, like when we get to the router's configuration, if you assign it an address that someone else already has on that Ethernet LAN, it's going to tell you. It'll say, I heard an ARP request, or I heard an ARP reply from someone else with this same address. So it's going to cause the switches not to be able to send the traffic between them. There's also some interesting cases, we'll see a little bit later when we get to security, that this could be a way someone could do what's known as a man-in-the-middle attack, or an MIM attack, to try to redirect traffic like from your default gateway to me, and then I could look inside the data from the source to the destination. Like if I'm trying to steal someone's passwords or whatever data that's in the network. And there's different ways that we can prevent this at layer 2. We'll get into more details. Mohammed?
Yeah, my question is, can I still maintain wire speed if I do routing on a layer 3 switch, since it has the ASIC coverage?
I'm sorry, can you still maintain what?
Wire speed, line speed, same line.
It depends on the platform. So some of the higher level platforms you can. It also depends on what type of features that you run at the same time.
Okay.
So the more features that you add, like when we talk about QoS, if you have a very complicated quality of service policy that says I want my voice traffic to do this versus my data traffic to do that, for every layer that the device has to look in, and if we were to consider this in the case of like the OSI model. So with the OSI model, we have these 7 layers. At layer 1, your physical layer, this is where your physical cables would be, or like wireless would also run here when you're looking at like your actual radios. At layer 2, this is where we would have our Ethernet switches, or where we would have frame relay, or PPP, or ATM, like some of our WAN protocols. At layer 3, at the network layer, this is where we have IP version 4 and IP version 6. At layer 4 of transport, this is where we would have TCP and UDP. Then the other ones, 5 through 7, this is going to be the application. Now what you need to think about is that every time a router or a switch makes a decision, it has all these potential layers that it could make its decision on. It could be something as simple as the physical layer, like in the case of a hub, just takes your electrical signal and just repeats it out another interface. Where a layer 2 Ethernet switch would normally look at the source MAC address and the destination MAC address, and then figure out where I'm going to send the frame based on the destination MAC. Layer 3 router is going to have to look in the IP header to look at what is the source, what is the destination. We could also include the TCP or the UDP ports. We could also include the application level things like an HTTP GET or an HTTP POST, which you would do with like your application caching engines and stuff like that. But when you look at this from like a programmatic point of view, it's going to take more resources to look deeper into the frame for every feature that I want to run. So you can actually tell the router to make its decision based on this information at layer 7. But the problem is it takes much more processing power to do that, because I have to make my decision at layer 2, then I have to make my decision at layer 3 and 4, and so on and so on and so forth. Where you can technically do it, but the more features you add, the slower the forwarding is going to be. So this is typically why you would use some sort of application, like Cisco has like that ACE module that's used for layer 7 forwarding. Or for, if you wanted to do something really advanced at your layer 4 decision, you would want to use something maybe like your 7600 or like your ASR, some really powerful router so it can make that decision. It's really going to depend on the platform. But anytime we get above layer 3 routing, this is where the enterprise platforms like the ISRs or ISR2s, you can make this decision, but it's going to be at an extreme performance hit. Exactly, yeah. And Cisco used to publish numbers on this. They don't really anymore, but there's kind of a useful document you can use if you look for Cisco router performance. These portable product sheets, it says that this document shows the raw switching numbers for 64-byte IP packets. And what it also says is that this is with no services enabled. So if you add access lists, if you add encryption, compression, etc., performance will decline significantly from the given numbers. Basically what this allows you to do is look at the different router numbers and then see where they fit in of how fast you need it to forward. Because if we look at like a low-level platform, let's say like an 1811 as ISR1, it says the packets per second that you can switch, or the equivalent of megabits per second, even though you may have a fast Ethernet interface, it says the best case forwarding is going to be 35 megs. So because the CPU is too slow and it doesn't do a hardware implementation, you can't get line rate when you use this platform. It's really only when you get into the real high-level ones, like the last one that they show here is 7600 with SOUP 720 says that you can get an aggregate of 15 gigs, where when you look at the service provider platforms like the GSR at the Engine 4 line card, it says that you can get 10 gigs, because for an Engine 4 card, the fastest speed is either 10 gig E or OC 192. So you get 100% line rate because it's hardware accelerated to do that. But the problem is, when you're looking at the enterprise, you're not usually using this platform. So you're going to be using something else mid-range, like maybe 2900 or 3900, where when you look at these, you take a huge performance hit when you try to run those applications. So with 38, let's say 3845, it says best case scenario, you're going to get an aggregate forwarding of 256 megs, but that's with no features. So if you turn on network address translation, it's going to go down. If you add an access to the interface, it's going to go down. If you do something like NBAR for layer 7 classification, it's going to take a huge, huge hit.
That's just for the 1 gig port.
This is aggregate across all interfaces. All interfaces. So this is just how fast the CPU can forward. And the problem is, these aren't really practical numbers, because this is for 64-byte packets, which is your smallest size. So when you look at like your web browsing, usually a normal day-to-day application is going to try to use as large of a frame size as possible. So the numbers are going to even go down from here.
So you're saying if it had like four fast Ethernet interfaces, the best it could give you Super 6.
Right, aggregate between all of them, yeah. And that's one of the main differences between the layer 2 switches versus the layer 3 routers. If you can keep your network to make the decision as low level into the frame as possible, the faster you're going to be able to forward. So if you can decide just based on the Ethernet frame, 99% of platforms are going to support wire speed for this. Like you can actually get a 10 gig link that'll run at 100% utilization. But as soon as you have to start looking at not only the MAC address, but also the IP address destination, it takes more processing power to do that. And then if you look at layer 4 information, and on and on and on.